Okay. Okay. Let's continue. So while preparing for sort of my notes for the last few lectures, I think I sort of got really excited to talk about celestial amplitude, so I really do want to get there. So the goal is for today, well, let me review what we did last time. Last time I derived the symplectic form for gauge theories. I derived it in flat. I derived it just for free Maxwell gauge theories, but in fact, all the calculations that I'm going to do today apply identically to any gauge theory that you ever, any abelian gauge theory that you'd ever want to write down. Essentially, it turns out that when I add interactions to my Lagrangian, of course that omega changes, but when you take the limit to Scri plus, all of those extra terms drop out completely. So the only thing that survives is the other things written up there. Okay, I introduced these nice set of coordinates, the flat null coordinates, which I introduced in general dimensions. But today I'm going to do everything in 4 dimensions. And in 4 dimensions, there's a nice set of complex coordinates where essentially z is equal to x1 plus I x2, the standard way. And so that the coordinates on the sphere you can rewrite in terms of as dz dz bar. And the goal of this lecture, the first part, is to use large gauge symmetries, derive the Ward identity for large gauge symmetries, and prove that it's exactly equal to this last identity, which is of course the soft photon theorem. Okay, and then hopefully if I can do all of this today, we can start talking about celestial amplitude in the last 2 lectures. Okay, so so let's start. So the first thing to do is all I'm going to do. Remember, I took a Scri plus or Scri minus in these coordinates are located at r goes to infinity, keeping u, z, and z bar fixed. Okay, so what I'm going to do is I'm going to essentially just take that symplectic form and choose my sigma. Let's choose this sigma to be Scri plus. Now, perhaps one important thing to remember is that Scri plus, as I said, it's a null slice, so it's not by itself a Cauchy slice. You do have to include I plus as well. But since I'm trying to construct just the gauge field sector of the symplectic form, which is massless, so I only need to talk about Scri plus. If you also have massive particles in your theory, then those data ends up on I plus, and then to construct the phase space for massive particles, you need to discuss I plus. So I'm just going to ignore massive states for now. Everything will be massless. So all I have to do is take my sigma and set r equal to infinity in this with this choice and simplify. Okay, hopefully this is an exercise that you know how to do. It's just a matter of writing out forms in particular set of coordinates. And the explicit answer that you get okay, so of course, there's an integral over sigma, and in this case, the coordinates on Scri plus are just u, z, and z bar. So I end up getting an integral over u, z, z bar. Another thing is that there is a measure which is coming from the determinant of this metric, which essentially is r squared. Square root of the determinant is r squared, but this quantity in index notation is roughly del a delta prime f a b, and these I have to lower this index with the inverse metric on the sphere, and the inverse metric on the sphere contains an extra factor of 1 over r squared. So the factor of r squared coming from the measure cancels the factor of 1 over r squared that you get because you have to lower this index. So no factors of r squared, and I can just take the r goes to 0 limit, r goes to infinity limit, and I get okay, so obviously omega has to be real, so if I ever forget it, you always add complex conjugates to make things real.
So if the r factors cancel, it looks like any null slice would work, not just correct.
Yeah, you can construct the Cauchy slice on any null slice, or on any constant R slice. But as I said, this was derived for abelian, just pure Maxwell, free theory. Then of course that's true anywhere, on any constant slice. But if I add interactions, like f to the 4, d phi squared, you add interactions with scalar fields and whatnot, then in general there will be extra terms over here. But all of these extra terms go to 0 when I take the limit of r goes to infinity. Because extra terms carry extra derivatives, and each derivative gives us an extra factor of 1 over r. So when I take the limit as r goes to infinity, they all drop out. So that formula was not exact because it receives corrections. This formula is exact. Once you take the large R limit, this is an exact formula. It applies to any abelian gauge series. In fact, the generalization to non-abelian is very simple. Just put a trace over here, and then it's non-abelian. It's also true there. Okay, so remember the whole goal of this stuff is to keep careful track of boundary terms. So to do that, what I'm going to do is take my AZ, this gauge field AZ, and I'm going to break it up into two pieces. So I'm calling this piece AZ hat. I'll define it for you in a minute. And an extra piece which I'm calling del Z of C. This is the boundary part of the gauge field. Essentially all I'm trying to do is I'm trying to separate out bulk degrees of freedom, boundary degrees of freedom, just so we can be really clear about what enters the phase space where and how. So this A hat is defined so that it vanishes on the boundary. And everything else I've pulled out into this piece over here.
How do you know it's a total derivative?
Good. How do I know it's a total derivative? Here, this is a simplification that I'm doing. It's physically realized. Essentially, C on the boundary, or the field strength on the boundary, captures the total magnetic charges in my theory. I'm going to assume, for the sake of this lecture, that there are no magnetic charges in my theory. Everything is just electrically charged, in which case the field strength on the boundary vanishes. So the gauge field on the boundary has to be pure gauge. So it's del Z of C. Okay? But if you did have magnetic charges, you can do that. You can derive a corresponding magnetic soft theorem as well. There's a very nice story with extra magnetic symmetries, which sort of complexifies your U1 symmetry. All technical details, very interesting. Essentially follows the exact same type of qualitative argument that I'm going to make here. So I won't talk about that separately. Okay, so let's plug this into this action, separate out things in terms of bulk and boundary terms, and see where we get. Oh, remember, so just to be clear, even clearer, this depends on U, and of course it depends on ZZ bar everywhere. This also depends on U ZZ bar, but this is just the boundary contribution, so it only depends on Z and Z bar. So it has no U dependence. Okay, so let me plug that in over here. So FUZ involves the U derivative of AZ. So this boundary term, because it's independent of U, will never show up over here. So the only place that I need to worry about is this piece right here. So essentially when I break it up, I'll get a contribution from A hat plus del Z of C. Let me define this. Where NZ is the integral over U of FUZ. So notice that it's a non-local mode, but this is important. So let's understand where this comes from. So I essentially took AZ originally, broke it up into A hat and CZ. This part doesn't depend on U, so the U integral comes all the way in and acts on F, and the integral over U of F UZ is, I'm just defining this to be NZ. Cool? Okay, let's now integrate by parts in Z bar. In this integral, I'm going to move over on this side. So I'm going to forget about the bulk piece for the moment. The interesting stuff is going to happen on the boundary. So let's integrate this by parts. Forgive me, I'm going to do something that I've been told explicitly never to do, but I'm going to manipulate equations by erasing stuff and rewriting them. But So I know I'm not supposed to do this, but in the interest of time, I get a minus sign, I get a C, and I get a del Z over here. So let's put out the delta outside, and I get a del Z over here. And let's now keep track of the CC part, the plus complex conjugate part. And then there's this minus piece. Okay? So of course in general this is in general del Z and Z bar is a complex number. But notice that only the real part of this is entering the symplectic form. The imaginary part is nowhere to be seen. Therefore, in order to make the symplectic form invertible, as always, we have to get rid of that mode. We have to gauge it away. Okay, so I'm going to gauge it away by setting the imaginary part of del Z and Z bar to 0. That's required in order to make the symplectic form invertible. Okay, so the only mode that's entering the symplectic form, let me perhaps show this argument. Suppose I had an omega such that the coordinates on my phase space are x, p, and x1, but my omega is given by dx wedge dp. So in terms of as a matrix, what does omega look like? So in the x, this is 0. In the xp direction, it has a minus 1. It has a minus 1 and a 0. Whereas there is no x1 term in my omega, so these columns are entirely 0. So this matrix is clearly not invertible. Make it invertible, what do? I get rid of these rows completely. Now I have a reduced phase space. And the reduced phase space is obtained by removing x1. That's exactly what I'm doing here. The analog of x1 is the real part is entering clearly because of plus complex conjugate. The imaginary part is not, so I have to remove it. So I remove it by setting it to 0. Okay?
If you were removing stuff like quotienting or gauge transfer.
Equivalent, it's the same thing. Essentially, I'm setting it to 0. You can also say I'm making it equivalent. It's a gauge condition. You have to gauge it away, and to do so, you have to choose a gauge condition. It's the most convenient gauge condition.
So there's some Lorentz gauge. Okay.
It's not exactly that. But here's why this is a nice gauge condition, is because this means that NZ is del Z of N. That's why this is a nice gauge condition. All right. So when I plug this in here, what do I get? I essentially get
as a gauge condition, are you imposing this only on the boundary data, or
just on the boundary. Everything is, all of this is just on the boundary. Okay, we're basically done. Now I have a nice symplectic form, invertible symplectic form. I have a bulk piece which depends on this a hat. This FUZ, remember, FUZ is just the u derivative of a hat. So this is just the u derivative of AZ bar hat, and there was a delta prime out there. So anyway, so this defines my symplectic form on the a hat modes, and then I have a separate symplectic form on the C and the N modes. Importantly, the bulk sector, the boundary sector completely decouples from the bulk sector. They're totally independent of each other. So I can find the Dirac brackets. What do I have to do to find the Dirac brackets? I need to invert the symplectic form. I can invert this separately and invert that separately. And every other cross Dirac bracket will just be 0. Okay, so I'm not going to tell you how to invert it. That's an exercise. But here's the answer. And let me just directly write down the quantum commutators, because the next step will anyway be canonical quantization, which I hope you all know how to do. All I have to do is take the Poisson bracket and elevate it to minus I that. So I'm just going to do that all in one go. So what I get is F UZ. It's more convenient to work in terms of the field strength. Did I miss this bunch of stuff? 2 over E squared. There should be 2 over E squared in front of that integral. On the other hand, the commutator for n and c, so n evaluated at z, c evaluated at z prime, is log. So this should immediately remind you of a 2D boson. In the last lecture in this series that I'm going to give, I'm going to in fact show you, I'm going to construct an effective action for these soft modes, and they will be precisely described by a 2D free boson. That will be a very cool map between T duality in 2 dimensions and electromagnetic duality in 4 dimensions. Okay, but anyway, so we haven't gotten there yet, but this should already remind you of that, the fact that the commutator is a log. And of course, everything else is 0. Okay, any questions? Please tell me if I'm going too fast or you're not understanding. I am trying to finish this section here, so I'm skipping a bunch of calculations, but I've put it all into smaller exercises which you guys can go through if you want to understand how to do the calculations. Okay. Because I keep calling this soft, but I haven't told you why I'm calling it soft. Remember, soft meant 0 energy, but I haven't told you why it's soft. To do that, I need to construct a Hamiltonian and check whether these modes have 0 energy. That is, do they commute with a Hamiltonian or not? Only then should I be calling them soft. So let us construct the Hamiltonian first.
So these are not canonically conjugate variables, right?
N and C are canonically, they are canonically conjugate. Strictly speaking, what you should say, because of the log, this corresponds to IR divergences as always. The well-defined variables are the derivatives. So if you take del z of n and del z bar of n, c, then you get a delta function. So the canonical conjugates are del z n and del z bar c.
So basically integrate.
Yeah. But as always, despite the fact that phi, the 2D free boson, is not an actual operator, it's a very convenient variable to work with, because I can construct e to the ic, which I will construct, and that will be the coherent state that you need to dress your external states with in order to get a finite S matrix.
And the F does not commute with itself because you're on this null slice?
F, this is Z and Z bar, so the opposite helicities commute with each other. So opposite helicities do not commute, but the same helicities commute with each other. This is reminiscent of the fact that this will also turn out to be true in the non-abelian gauge series. So when I take multiple soft limits in non-abelian gauge series, as long as the helicities are the same, everything commutes and is really nice. And that's coming from the fact that all of these things nice and commute. Okay. So in order to construct a Hamiltonian, because I'm working in these funky coordinates, the first step is to figure out what the Killing vectors are of these. So I'm not going to ask you to compute Killing spinors, but hopefully you know how to solve Killing vector equations, and I don't have to go through the details. So let me just tell you what the Killing vectors are in these coordinates. Essentially Poincare group, as we all expect, but because it's some funny coordinates. Well, they're funny if you're a bulk guy who likes to do calculations in the bulk, but from the boundary point of view, these are fantastic coordinates because they make the isomorphism between SL2C and Lorentz group manifest. So here f is a function of the form A0 plus A1z plus A2z bar. So these are the 4 translations. And Y is a vector field, holomorphic vector field. So alpha plus beta z plus gamma z squared. Of course, they generate the global SL2C transformations. Towards the end of this lecture, I'll talk about asymptotically flat spacetimes. Then this will be elevated to an arbitrary function. That's called super translations. This will be elevated to an arbitrary holomorphic vector field. That's called super rotations. Those are the set of enhanced symmetries that you get for asymptotically flat spacetimes. But right now we are in just plain old flat spacetime, so we should reproduce Poincare, and this is Poincare.
Can I view this from the point of view that there is a sphere as the global conformal transformations?
Yes, exactly. That's what this is.
Can you explain again what f is?
Well, it's just this function of z and z bar that's showing up in this vector field. I've written it in a very suggestive way because it's going to generalize nicely later on. But there are two sets of killing vectors. This one is the translation killing vectors, and these ones are the Lorentz transformations. And I've packaged everything into a function f over here, which is defined here. So there are 4 independent parameters corresponding to 4 translations. This A0 is time translations, and these are spatial translations. And then I have a vector field y that's showing up here. There's a plus complex conjugate. And that vector field, the holomorphic part, is simply given by these alpha, beta, gamma, or complex numbers in general. So these are 6 rotations. 6 Lorentz
How would you
transformations.
interpret the f symmetry on the celestial sphere? The y part?
That is the problem. That is the biggest question out there. And this is the thing that makes CCFT super hard. It's the translation part. So what we do this really nice thing with CCFTs where we make the Lorentz group manifest. So this becomes literally the global SL2C, but that really makes momentum space complicated to look at.
Complicated because it's not in the SL2C representation, or
Well, you can no longer look strictly speaking at SL2C representations. You have to look at BMS representations when this generalizes, which is an infinite dimensional group. It's a much more complicated representation theory.
Then on the celestial sphere we don't have a CFT. We have something that is...
That's my point. I never said it's a CFT. I said it's a CCFT. I always say, I try my best to say CCFT. I apologize if I ever said CFT. We don't know what the structure of this CFT is. I think I started out my lecture saying this. So I'm essentially just starting from things I know, which are Poincare, S matrices, and just building up from there. Okay, so we can construct the charges for this just like I showed you. I told you how to do that last time. Maybe I'll remind you. What you're supposed to do is you're supposed to take omega delta psi, which is a particular charge, particular transformation whose charge you're trying to compute. And if that symmetry is canonical, which in this case it will be, you will get something that looks like this. Where in our case, delta psi of A is just the Lie derivative of A. Lie derivative with respect to this vector field and that vector field in order to get Hamiltonian and the rotation generators. Okay, so the Hamiltonian for for translations with that function f is simply given by 2e squared and then j of y So the only thing I want to point out over here is that only the f part enters here. None of the soft modes enter, which means because f and the n and c completely decouple from each other, this means that the commutator of pf with n and the commutator of pf with c is just 0, which means that these operators carry 0 energy. Consequently, in the quantum theory, they label an infinite dimensional vacuum Hilbert space. However, notice that these n and c's are showing up in the angular momentum charge, so they don't have 0 angular momentum. That is to say, when I construct the vacuum Hilbert space, the vacuum states will carry angular momentum. They will not be Lorentz invariant, but they will all have 0 energy. That is the sense in which they are the vacuum state.
We're missing an f in the PF.
Yes. Okay, let us quantize. So this is the old canonical quantization. What do I want to get rid of? Okay, so I'm not. Let me just first and start off with the FUZ because that's perhaps more standard, and you won't be surprised. So the best way to quantize it is to rewrite that algebra in terms of an algebra that you're already familiar with, and then I won't have to tell you how to quantize it because you've done it a million times. So I'm going to define this operator some number, I don't care, over omega. So all I'm doing is defining the Fourier transformed operators with respect to u. And then there's a similar thing for minus with z bar over there. Okay? And these operators satisfy the following algebra. Essentially, all you need to do is, I'm writing down this commutator with a dagger. So it's very easy to compute this. You replace each of these with the Fourier transforms, you get a commutator of the f's, then you just use that algebra over there, do the omega integrals. What you get okay.
How do you find these operators again?
I'm coming to it one minute. You saw this doesn't look nice at all. However, let me define the following object. P mu is omega, the real part of z, imaginary part of z. This is just a definition, and this is an exercise for you guys. If I write this, of course this satisfies p squared equal to 0, so it's a null momentum. Exercise for you guys, check that this quantity on the right is nothing but 2 pi 2p0 delta cube of p minus p prime. So these operators are just creation annihilation operators, that's what they are. This is the first place where we are seeing a localization between space-time and momentum space. Remember, the z's that were showing up on this side are the z's showing up in the field f, and these f's were obtained by taking a limit out to square plus. So they are space-time points. So the z and z bar labels a point on the space-time sphere. However, when written in this form, the z is labeling a point in momentum space. Now usually we think if something is local in space-time, then it's horribly non-local in momentum space and vice versa. But this is not true on square plus. When you take the limit to square plus, because of something called the stationary phase approximation, you have a localization between momentum space and position space. Consequently, the celestial sphere, which is often defined using momentum space amplitudes, is the same thing as the space-time boundary of I plus, the celestial sphere in space-time, because of this localization, which is a special feature of Scri plus. Okay, so I hope I don't need to teach you how to quantize creation annihilation operators, just due to Fock space stuff. The thing I do need to tell you, of course, is the vacuum state. Usually people say there's a unique vacuum state, so we define this vacuum state to be annihilated by annihilation operators, but now we don't have a single vacuum state, so I need to tell you about the vacuum Hilbert space. Okay.
Is it consistent with the uncertainty principle? You said both localized momentum and position.
Yes, yes, because it's at infinity. It's not really local. Well, it's not entirely local because there's a u integral involved. So it's definitely not completely local. There is a non-locality in the null direction. This is also a feature because this is important because Scri is a null boundary. So this localization won't even happen on I plus or I0. This is often happens with null boundaries. There's things called ultra locality, where like field theories just break up into subsectors of theories into various null slices. These are nice properties of null. Okay, so let me just talk about the vacuum Hilbert space can also be really simply constructed. And notice that C commutes with itself. Of course, also N commutes with itself. So I can choose any of these operators to construct a basis. I'm going to choose C. The reason for that is when you generalize this to non-abelian theories, C still commutes with itself always, but N no longer commutes with itself. And so this will not generalize if I do with N. Of course, in the abelian case, you can do both. So it's very simple. I'm going to define C, and I'm going to define a basis state and then I can use that algebra to work out the action of N on this state, which is not what I have in my notes. My notes are wrong, but it's easy to work out what it has to be. Ln z minus w so this is an obvious statement. N and C are essentially conjugate to each other, so if C is like X, then P has to be derivative with respect to X.
Is this the phi?
Hmm?
Are you taking generic state or?
This is a generic basis state in the vacuum. Of course, now a generic vacuum state is just obtained by integrating using any wave function. The main point of this exercise is to impress upon you that there is an infinite vacuum degeneracy, not a single unique vacuum state, but infinitely many of them. And now all of this I did on a single scry, like scry plus or equivalently scry minus, the calculation is identical. Now I'm going to start talking about S matrices. So usually we talk about S matrices as an in-state overlap with an out-state. But now I need to also tell you about the in vacuum and the out vacuum. So the correct definition of an S matrix in gauge series is to specify a vacuum state, then you specify some set of out creation operators. So these are the out creation operators. Then you have to specify a bunch of in out annihilation operators and in and you also have to specify an in vacuum. This is the most general S matrix that we should be considering under gauge transformations, in gauge theories. And in particular, one of the assumptions, of course, that we make in QFT is that the in vacuum and the out vacuum is unique. Oh, I should tell you which is the QFT vacuum out of these. As I said, there's infinitely many vacua. The QFT vacuum satisfies another nice property. We know, we assume it's Lorentz invariant. So if you just look at that, there's only one Lorentz invariant vacuum. Is this phi equal to 0 vacuum, which I'm just going to simply denote as 0. This is the standard QFT vacuum. You can check because C acts on phi equal to 0, it just gives you 0. So when phi is 0, that particular vacuum state is a Lorentz invariant and also Poincare invariant because it has 0 energy. And so this is the QFT vacuum. This is the one that we just assume in QFT.
So, then F acting on any of those steps, phi is trivial 0.
Yes. You have to, of course, this is canonical quantization, you have to do normal ordering. But yeah, once you go through all of that standard process, it all acts on it and gives us 0. Questions? Anyone? Okay. So, I'm now going to take this amplitude and derive a Ward identity coming from large. I haven't constructed the large gauge charge yet. I'm going to do that, plug it into the S matrix and derive a Ward identity. The thing that I'm going to find, so I don't know if I'm going to derive it in that language because my end goal is to derive the soft photon theorem, but the thing that you find usually is that the Ward identity tells you that phi in cannot be equal to phi out. They must be different, and they must be different in a very particular way. And the fact that we assume that they're equal is precisely why the S matrix is 0 in gauge theories. The Ward identity tells you that unless phi in minus phi out is equal to some function that is specifically fixed, the S matrix should be 0. and we just assume phi in and phi out are equal, and that specific function is not equal to 0 identically, so we'll find that the S matrix has to be 0. That's exactly what we were finding when we were doing IR divergence calculations. That's the reason for it. If you keep track of the shift in the vacuum, you'll get a nice and IR finite vacuum, which will be the topic of the last lecture. I'll derive that not using this space-time language, but using effective actions on the CCFT side, using a different formalism.
You don't use the Lorentz invariant vacuum. How do you get Lorentz invariant amplitudes?
You don't. No one said that your vacuum S matrix has to be Lorentz invariant. It has to be Lorentz covariant. And in general it is, because these things are not Lorentz invariant, they're Lorentz covariant. Now all I'm saying is that on top of the operators not being Lorentz covariant, the vacuum states are not Lorentz covariant either.
Tree-level amplitudes like anything.
The amplitudes you compute in quantum field theory are always computed in this vacuum.
Yes.
So they're always going to be Lorentz covariant in the sense that they will transform in whatever way these operators transform. The vacuum will not contribute anything.
Like, okay, you have Lorentz generators in Merton space,
Yeah.
and then you take the sum of all Lorentz generators, that annihilates the vacuum. That annihilates the amplitude, the final answer for the amplitude.
Yeah,
So
that's the
if
statement that is covariant.
Lorentz covariant.
The amplitudes you compute using Park-Taylor formula and all of those things are not these general amplitudes.
Okay.
They are the amplitudes where phi in is equal to phi out is equal to 0.
Right, and those don't make sense at loop level.
Yes.
Because of this infinite divergence.
Exactly.
So do you
They're only at tree level they make sense, but that's obviously not the full amplitude.
So do you have to modify the Lorentz generators take them in appropriate representations?
You don't modify the generators, you just modify the fact that the vacuum itself. This happens in spontaneous symmetry breaking all the time. You can have a perfectly well-defined symmetry of an action, but the vacuum breaks that symmetry. However, I refrain from using the word spontaneous symmetry breaking here is because in typical standard spontaneous symmetry breaking, there are superselection sectors. There is never a finite energy process that can map you from one vacuum to another vacuum. And therefore, once a particular vacuum is chosen, then we are going to remain in that vacuum forever. Here, it's not what happens. Every finite energy process changes the vacuum. So it's sort of similar, but also different. So you have to keep in mind. Okay, let's just derive the Ward identity. I have, how many, 20 minutes? I started a bit late, I hope. Okay.
Yes.
Okay. So far I've been talking about Scri plus or equivalently Scri minus. One of the surfaces. I've quantized the phase space, or rather now that I've done quantum mechanics, I've quantized the Hilbert space on one of these slices. Now I want to talk about an S matrix. But to do that, I need to connect Scri plus and Scri minus somehow. And unless I can do this, there's no way for me to proceed further. In fact, this was precisely the status of all of this stuff in the 1970s. People had discovered all of these charges and all of these symmetries all the way back in the 1970s. The thing they didn't know how to do was to connect Scri plus and Scri minus. And it wasn't until 1993 when Christodoulou and Kleineman wrote their Magna Carta 300-page proof of nonlinear stability of Minkowski space, where maybe there's like 2 pages in that 300-page proof where they have to describe how to connect Scri plus and Scri minus. Once you have this, then you can start talking about how to apply all of these concepts to an S matrix. That's one of the reasons this is sort of a new topic, is because people were interested in this stuff in the 70s, and then because they didn't know how to connect Scri plus and Scri minus, completely died away. And I think the work by Christodoulou and Kleineman is great, but its relevance to this topic was not appreciated until Andy figured that out, that there's that connection that we can now exploit. Okay, what is that connection? How do we connect Scri plus and Scri minus? Now let me go back to the drawing that I drew before. Scri plus, Scri minus. So the natural point to do this is to just map it across I0. So there's this boundary, Scri plus minus. There's this boundary, Scri minus plus. And you might as well think, maybe there's some field on Scri plus minus which is equal to the analogous field on Scri minus plus. And that's indeed what happens. And the way to sort of derive this from first principles, and I'm not going to do that, is to consider de Sitter foliations of Minkowski spacetime. So these are de Sitter slices. you solve your equations of motion on these de Sitter slices, you take the limit out to spatial infinity, then you take the limit out to the future of spatial infinity and the past of spatial infinity, and you this what I'm going to call the antipodal matching condition pops out of that entire calculation. The end result is the following statement. Actually, now that I'm going to write this, you guys are immediately there is something wrong in what I said earlier. Earlier I said that these two vacuum states have to be different. Now I'm saying that they have to be the same. What I said earlier was wrong. It's not these two vacuum states, it's the vacuum states that diagonalize n, which I didn't talk about here. I chose to diagonalize the operator C, but I can equivalently diagonalize n because n commutes with itself. And there's some basis states for that n. In that case, n in and n out don't commute with each other. That's the statement. It's not true for these phi states, but it's true for the n states. Okay, these are the matching conditions that show up.
The phi out in these new matrix are equal.
Yeah.
Okay.
What was the question?
Basically phi in is equal to phi out. That's the matching condition here. So
Are the creation operators, the out creation operators and the in creation operators different?
they are different.
Then when you define the Fox,
The creation operators always annihilate the vacuum. The question now is, now I have infinitely many vacuum states.
so
So
annihilate all of them? All
yeah,
of them?
every single vacuum state is annihilated by. So the idea is now the structure you should think of is there are infinitely many vacuum states. You choose one vacuum state and then you build a Fox space on top of that. You can choose a different vacuum state and you get a different Fox space on top of that. So you have infinitely many Fox spaces.
That works because N and C commute to that. Which is
Yes. Now this generalization of non-abelian gauge series, because as I told you, n does not commute with itself. So what is the corresponding statement and resolution of Ia divergences in non-abelian gauge series? I don't know. No one knows. It's an open question. If you can solve this, this would be like the particle physics people would really appreciate having a symmetry interpretation of non-abelian Ia divergences, but it doesn't exist so far. Okay, so two things to note. Firstly, remember the special way I set up my coordinate system. The ZZ bar on scri plus is antipodal to the ZZ bar on scri minus. So this is not a same angle matching condition. This is an antipodal matching condition.
But it looks the same in this coordinate.
It looks the same because of my clever choice of coordinates. This is what makes these coordinates nice, despite the fact that I'm trying to impose some crazy antipodal thing as far as the coordinates are concerned. It's just f of z equal to f of z. It's a very nice system. Okay, now I'm going to use these matching conditions to derive the Ward identity. Actually, I'm just going to need this one. I don't even really need that one. So the first step is to construct the charge. Remember what the charge was? Remember, I think the charge was 2 over e squared integral lambda star f. So if I work out what this is in these coordinates is d to z on scri plus minus. Remember, this is on the boundary of sigma. So boundary of scri plus is scri plus minus lambda fur. And there is a so this is the charge on on q plus on scri plus, and there is a similar charge on scri minus where the boundary is scri minus plus. But notice that f is being matched. Therefore, because of the matching condition, this tells us that q lambda plus is equal to q lambda minus. This is the statement that the charges are conserved in the S matrix. The incoming total, this is not the total charge. Remember, lambda is an entire function. So when lambda is equal to 1, this goes back to the normal u1 charge that you guys are aware of and familiar with. So for lambda equal to 1, this would simply be the statement that total incoming charge equal to total outgoing charge. But now that lambda is a function, This is a local conservation of charge. The incoming charge at a particular angle is equal to the outgoing charge at the antipodal angle. So it's at every angle there's a conservation law. It's infinitely many conservation laws, which makes sense because it's infinitely many symmetries generated by a function.
Nothing to do with Wartag-Ayas identities.
It is. This is the S matrix version of.
Wartag-Ayas identities.
Yes.
Okay.
Okay. So we know this. However, we had another representation for the charge. I think we did. Did we derive it? Let me write it down and tell me if you guys, if it. So maybe I can just derive it right now. So the other representation for the charge is Q lambda is on the boundary, lambda star f. So I can obviously, using Stokes' law, I can write it as an integral over all of sigma d of lambda star f. And then this can be written as an integral all over sigma. This is d of lambda wedge star f plus integral over sigma lambda times d star f, but d star f is Maxwell's equations. So this is star j, just the current. So this is just another representation of the same charge. And we know the full charge is identified, so this full charge on scri plus should also be identified with a similar charge on scri minus. So let me just call this, for reasons that will soon become clear, Q hard, and this part is Q soft. And then
Minus scri plus.
I haven't specified what sigma, this is true for any sigma. I'm now going to okay. So the equality of charges over there is the statement that Q hard plus S plus Q lambda plus H is equal to Q lambda minus S plus Q lambda minus H. That's obviously true. And now I'm just going to move all the soft pieces to one side and the hard pieces to the other side. So again, I'm going to do what I'm not supposed to do. So move this soft part to this side, I get a minus sign, minus S, and move the hard part to this side, minus sign, Q plus hard. Okay. Let us understand the structure of each of these sides, and that's going to be the end of my talk for gauge series. And then in 5 minutes, I'm going to tell you about the BMS group. Yeah, I can't talk about celestial holography and not introduce the BMS group. That would be blasphemy. So I have to do it. Okay, so let's understand the structure of both sides. So what I'm going to do is now, this is an identical equality. It's coming from this equality here, which was coming from the matching conditions, which is coming from Christodoulou Kleinemann's insane work. Well, he did it in gravity. This is, of course, the gauge 3 analog. It's easier to do. It's flat space-time. You could do this. It takes like half an hour of calculations. But in the gravity case, this is a big deal. So now what I'm going to do is I'm going to take this equation, this full equation, and sandwich it in order to obtain some S matrix formula between in and out states. And right now, for simplicity, I'm going to assume that the vacuums are the standard QFT vacuums, but you can generalize all of this to these general 5 vacuums, and you can get a much more general Ward identity. But I'm just trying to, my goal, as you remember, is that I'm trying to derive the soft theorem. Soft theorem was derived using Feynman diagrams. So there, the assumption was that I'm working in the standard vacuum. So that's my goal. That's why I'm just going to assume that these in and out states are defined with respect to that standard vacuum. But you can generalize this very easily by just changing the vacuums in and out here in this formula. Okay, let me now understand this piece over here and what this is doing for us. Okay, so this piece over there was d lambda wedge star f. If you now work it out in these coordinates, this is integral d to z del z lambda, or let's say del z bar lambda, fuz plus. Now, but I wasn't putting plus and minus signs up there because there I wasn't distinguishing between square plus and square minus. But now I'm in an S matrix, so it's important to distinguish between square plus and square minus. So that's what this superscript means here. With the minus. So this is what this charge evaluates to. Remember, this is the soft charge. So all I've done is I've taken this entire piece, which is an integral over sigma. So it involves integral over z, which we are seeing over there. Then there's a d lambda. So that shows up as a derivative acting on lambda. And then there's a u integral. Remember, lambda does not depend on the null direction because lambda was a function that was originally defined only on the boundary of sigma. So lambda only depends on z and z bar. So when I have the u integral, I can pull it all the way in and I get this thing. This is of course nz of how we defined it over there. So I can obviously just replace this with nz. But I'm going to do something else, which is I'm going to use that definition up there and replace it with something in terms of O. What is that? What do I need to do? So anyone, what do I need to do to that equation in order to reproduce this term over here? Multiply both sides by omega, take omega to 0. Okay, so this thing is limit up to some numbers which I'm not going to keep track of. Omega to 0, omega O Is this clear to everyone? You take that formula, oh here it's a plus helicity because it's a z. So when you take the fuz up there, there's a 1 over omega factor in front. So let's multiply both sides by omega first. So now I get omega times O plus. Now I'm going to take the omega goes to 0 limit. That gets rid of the e to the I omega u. And I just get integral of du of fuz, which is the quantity that I'm interested in. Okay. But now this should ring bells. This is the soft theorem. What is the soft theorem? I told you again and again, in the soft limit you get a pole. You get a 1 over energy pole. So if I multiply by the energy, then take the energy goes to 0 limit, you pick out the residue at that pole. So you pick out precisely the soft factor. Because of course the statement is that in the q goes to 0 limit, that is the leading order term, but there's of course many other terms in the expansion. But by taking, first multiplying by omega and multiplying, taking omega goes to 0, you're extracting precisely that soft piece and killing off everything else in the amplitude. So this left hand side operator is precisely in terms of scattering amplitudes is doing something like it inserts a photon, it multiplies this amplitude by omega and then takes the limit omega goes to 0. So this is the left hand side of the soft theorem. All I need to do now is to massage this piece and show that it can be recast into the right hand side. So that's the final step.
The difference between both integrals?
Yeah, good question. These two are equal to each other because of CPT invariance. So I sort of inherently taken that, and this is equal, well, with the minus sign because the photon has negative parity. So this with the minus sign is equal to this. Factor of 2 has to be involved, you have to keep track of.
So when you calculate the differential form, you have other permutations of wedge.
Those are all
Or zero?
No. There's a del z term, then there's a del z bar term. The del z bar term I've written out.
Yeah.
There's a term where this del z acts on this, but now I can integrate by parts.
Okay.
I can bring this over here, bring this. Remember, this is nz, and nz is equal to del z of n, so it is itself a total derivative. So I can integrate by parts.
How about the u?
Lambda doesn't depend on u, so there's no u derivative. Good question. Okay, I am very late. So I'm just going to convince you that the last term has the right structure and make it an exercise for you to check it. So the last term actually is very easy to manipulate, really, it's not that hard. So lambda h minus is acting on, let me now take there's an out in state, of course, it has many, many operators in there. So let me just consider one of these states, P, let's say omega k, zk, z bar k. Okay, we know what this charge does. What does it do? It generates gauge transformations. That's how we constructed it in the first place. So all I need to figure out is what is the gauge transformation of this state, and then I'm done. But we just showed, I mean I showed it here for the photon, but of course all of this works out exactly for the scalar and stuff. So this operator over here, this state, is really just a creation operator, omega k, zk, z bar k acting on the vacuum. So all I need to do is compute this q hard commutator with this, and the q hard contains only the hard field, so it annihilates the vacuum. So I just need to compute that commutator. But this operator O is a Fourier transform of the field. And this is again where it becomes crucial that the momentum space localization is the same thing as the z in momentum space is the same thing as the z in position space. So this becomes very crucial here. So it's almost obvious what this is. This is simply I or minus I times the gauge transformation of this thing, which is I lambda z k z bar k times the original state back again, pk. Because I'm just doing a gauge transformation on the field. And gauge transformations act very trivially. Q phi is minus I delta lambda phi minus I times I epsilon phi, which is the gauge transformation of a charged scalar. I should have put in, sorry, Q. So of course the charge of the scalar is showing up here, so Qk. Okay, let's put it all together, write down the final formula, and then in 1 minute tell you about BMS. The final formula that we get, the left hand side is integral d to z del z bar lambda, a limit omega goes to 0 of omega O plus omega z inserted inside an S matrix. So all of this is inserted inside the S matrix. And then here on this side, I get back basically a sum over all of these sort of terms. So I get back a sum over k, qk, lambda of zk, z bar k times the original S matrix. Alright, so now this is exactly the form of a soft theorem. You take a soft limit on this side, you get a factorization into a soft factor and the original amplitude. Now to reproduce the precise form of the soft theorem, I have to get rid of this integral over z here, because in the soft theorem there is no integral in the z direction. It's very easy to do. You can just choose lambda equal to 1 over z minus w. Then when del z bar acts on this thing, you get a delta function. Integration localizes completely, and then I just need to substitute this lambda into here. So let me do that final step, and again I'm going to erase out stuff here. So now when I localize everything, this entire charge thing looks like sum over k, qk, z minus zk. This is exactly the soft theorem, because though it doesn't look like it, this thing over here is precisely pk dot epsilon over pk dot q. Exercise, check this. This is really simple, so I don't even need to really. All you need to do is use this momentum. Use this momentum parameterization I showed you. Plug it all in here.
So one question. What happens with different lambdas?
Yeah, good. So it looks like I have many more ward identities than soft theorems because I had to choose a particular lambda in order to reproduce a particular soft theorem. But that's not true. I did choose a particular lambda, but this lambda, this in some sense you should think of this as infinitely many functions, one for every point W. There's a one-to-one map. There are infinitely many soft theorems, one for every direction of the soft photon, every point on the sphere where the soft photon points. Remember, in the soft photon theorem, I'm taking the energy to 0, not the direction. So the direction is a free parameter. So there's one soft theorem for every point on the sphere. But there's also one ward identity for every point on the sphere because it's parameterized by a function on the sphere. So it's a one-to-one map between soft theorems and ward identities.
You can pick different kinds of functions.
You can pick different kinds of functions, then you will not get localized soft theorems, you'll get integrals over soft theorems. The original ward identity was just you take the soft theorem and you integrate over with respect to arbitrary function, and then you'll get some nice looking formula if you want. This is not, the point to remember is that it looks like it's a particular function, but there's an arbitrary parameter in here, W. So it's like an arbitrary function, but the function changes depending on which point on the sphere I am. So it's or maybe put it another way, this function is a basis on the space of all possible functions. So if you can show that the ward identity is satisfied for this, then it's satisfied for all possible functions because this is a basis. Anyway, there's many ways to see that that everything I'm saying here is literally just a one-to-one map.
So you're having some analytic function that is found within lambda?
Yeah.
You powers of lambda and you say,
Yeah.
order in lambda, it works.
Exactly.
That's an analytic number.
Yes, absolutely. Because I was assuming anyway that integrals over the spheres are well defined, so it has to be perfectly globally well defined. Okay, I really don't have any time. Maybe I should. All right, I won't take up your time now. For the first 15 minutes of the next lecture, I'll just sort of briefly tell you how this generalizes to. So in any case, let me just tell you, everything that I've said today, right now here, I've shown you explicit calculations for QED, and the reason I did that was, of course, the QED is the simplest non-trivial example where I can show you calculations on the board. Everything that I'm saying essentially just follows over in exactly the same way for gravity, for non-abelian gauge theories, for subleading soft theorems. The whole story is essentially just a generalization of what I've told you here. You just need to put in a little bit of extra effort to do calculations, not useful for like a 6-hour lecture series. So I'm just going to briefly tell you what happens in the gravity case when we come back after the break, and then I'm going to start talking about celestial amplitudes. Thank you.
I guess we have 20 minutes break, right?
So a weird question.